Okay. Before we talk about the derivative of an inverse, I want you to brainstorm about what you know about inverses from your Algebra 2 and pre-calculus days. Okay? So I'll give you about 60 seconds to converse about what you know about inverses algebraically, graphically, and numerically.
Switch for it, yeah. They're not reduced. Get y.
Like coordinates.
I don't know.
Oh, sweet.
Okay, algebraically, what do we do? Switch the x's and y's. I don't think that it's pertinent, no. Numerically, I'm going to switch to numerically. What do we do? We switch the x's and y's, okay? Graphically, technically, we still switch the x's and y's, but what's the special property that we have from the inverse to the graph? Oh, Trenton. Great work. Okay. So as a reminder, okay, and I don't think that you need to write this down, but I just want to go through some of these reminders. As a reminder, we have an inverse when, if we compose the two, they undo each other to be x. Okay? When we compose the two, they undo each other to be x. Examples of that would be the cubed root of x cubed. X cubed and cubed root of x are inverses of each other. When we compose them together, they cancel out to be x. Okay? Another example. That's not the same as that, but you get the point. Okay? When we compose the two together, oh, here we go. Maybe one that you could have had yesterday. The natural log of e to the x. Those undo each other to equal x. Okay? Or the one that really would have benefited you yesterday. Those undo each other to be x. Okay? You know what I'm talking about? Which problem that would have been helpful on? Okay? So, like I said, when we have inverses, the graph reflects about the line y equals x to get to the inverse. So if we were to graph e to the x and natural log of x, we would see that they are reflected about the line y equals x. Cubed root of x and x cubed would have that same property. Okay? Now, you learned this in pre-calculus. We talked about it for maybe a day or two. But there's a test we have to determine if a function has an inverse. Do you remember what that is? We have a vertical line test to see if it is a function. We have the horizontal line test. Okay, and maybe that's something that you want to write down so when we get to talking about our next thing, you understand what's happening. Okay? The horizontal line test tells us whether we have an inverse or not. Okay, I have 3 graphs up here. Graph number 1, does it pass the horizontal line test?
No.
No. So it does not have an inverse. It's a function, but it doesn't have an inverse because the inverse would not be the function. Okay, since it doesn't pass the horizontal line test, when I flip this about y equals x, that graph is not a function. It won't pass the vertical line test. That's really what's happening here, okay? Does this one pass the horizontal line test? What about this one? Yes. Okay, so these two would have inverses. Okay? We'll take about 3 minutes and talk about this. Okay? So don't write all of this down right now. Okay? So we say that an inverse function exists if our function is 1 to 1. And don't write that down. 1 to 1 means it passes the horizontal and the vertical line test. So every x has one y, and every y has one x. Okay? What we are going to do with our calculus that we know is this right here. We know that we have an inverse if it's strictly monotonic. Okay? Anyone know what that means? Okay. Okay? Functions that are going to pass the horizontal line test are always increasing, or always decreasing. And this is what we need here. If we have an inverse function that exists, in order to pass the horizontal line test, we're always going to be increasing or we're always going to be decreasing. As soon as we have that turn, we're no longer going to pass the horizontal line test. Right? If we have any sort of minimum or maximum, any sort of turning point, we are not going to pass the horizontal line test. Okay? Well, our derivative tells us where we are decreasing and where we are increasing, right? If our derivative is negative, we know that our function is decreasing. If our derivative is positive, we know that our function is increasing, right? So we can decide whether our function has an inverse based on what we know from the derivative. For example, I'm skipping one second, and I'll come back to it. If we have, go ahead and write this down. F of x equals x cubed plus x plus 1. Okay? Julia, what's our derivative?
3x squared plus 1.
And what do we know about 3x squared plus 1? No matter what we plug in for x, what kind of numbers are we going to get? Okay. Our derivative is always going to be positive. Which means our function is always increasing. Okay? And since our function is always increasing, then f of x has an inverse.
The last two statements supposed to be f of x or the
F of x. Because if f prime is positive, then f of x is increasing. And we're really concerned about whether our function has an inverse? Okay. I was hoping that they would be here by now. Okay, so we'll talk about this one also. X squared plus 2x plus 1. Okay, so what would our derivative be? 2x plus 2. Is 2x plus 2 always going to be positive?
No.
Is 2x plus 2 always going to be negative? No. Sometimes it's positive, sometimes it's negative, like half and half, right? So no inverse exists. Okay? Since 2x plus 2 could be negative or it could be positive, okay? We have to be strictly positive for our derivative or strictly negative for our derivative. Okay? So the first part of your homework assignment is you deciding, does it have an inverse or not? Okay? Now we are not going to actually find the equation for our derivative of an inverse. It's always going to be at a point. Okay? Our derivative is always going to be at a point. But here is our rule for the inverse derivative. Okay, so the inverse derivative is 1 over f prime of f inverse of x. Okay, more than likely I'm going to ask you for like f inverse prime of 2 or f inverse prime of 3, or it's always going to be a number. Okay, so until we have to leave for our AP stuff, we're going to do problems over and over. Okay, and cross our fingers that our seniors get here eventually. Here's our first one. Go ahead and write it down. I had slides to like stand up, move to a new table, but we're not going to do that. We don't have time. Okay, do you notice how they only gave us an x value? They didn't give us a coordinate. Okay. I'm looking for f inverse of 3, but I have f. Okay? And that's going to be kind of an issue. Okay? What we first need to decide, this is the x coordinate for the inverse, which means what about our function? Is it the x coordinate for our function? No, it's the y coordinate. If this is our x coordinate for our inverse, then it's our y coordinate for our function. Okay? And I know that this isn't an equation we really want to solve by factoring, so let's use a guess and check method. What number for x can I plug in and we get an output of 3? What number can we plug in for x where we get an output of 3? I'll give you a hint, it's not 1. Right. 2?
Yeah.
8 times 1/4 plus 2 minus 1. Does that work? Okay. So what we know is that f of 2 equals 3. Which would also mean that f inverse of 3 equals 2. Okay. Questions on where we got any of that? We're going to come back to it. We also need to know what f's derivative is. And f's derivative would be 3/4 x squared plus 1. Okay. So now, why do we need all of that? Well, if we want f prime, f inverse prime of 3, then our rule is 1 over f prime of f inverse. That's our rule that I had you write down on the previous slide, right? Coming together, right?
It is.
Okay. What's f inverse of 3? 2. That's what we figured out before. Okay. So now all we have to evaluate is f prime of 2. Well, we have f prime written here in red. Pierce, when we plug 2 into that, what do we get? Yeah. Ask me a question. The coordinate on f, we switch x and y for the coordinate on f inverse. We need to know that for this piece right here. As soon as we know that, then all we have to worry about is plugging that number into the derivative, which is why I asked you to find the derivative.
Hey,
Yes.
I'm just lost in the. Where'd you get 1 from?
So f prime of 2, if we plug 2 into our derivative, 3/4 times 2 squared plus 1 gave us 4. And so I replaced my denominator with 4.
Okay.
Okay. Okay. We'll do this problem and then we'll head upstairs. And I guess our seniors will just have to watch the video. Hi, seniors. No.
Hi, guys.
Yay.
We'll see if they even watch it. They'll know that we said hi. What's nice about this problem? They gave us the entire coordinate. That's going to save us a step, isn't it? They gave us the coordinate so we don't have to think about finding that other piece of it. Which graph is the coordinate 7, 1 on? Is it on the inverse or is it on the function? Find the derivative of the inverse at 7, 1. Those are connected, wouldn't you say? If we're finding the derivative at 7, 1, that would deal with whatever the derivative we're taking. So we know that f inverse of 7 is 1, which means f of 1 equals 7. That's what we know from all of that. Okay. Let's do this real quick. Our derivative. Ethan, what's our derivative?
21x squared plus 3 times quantity natural log of x squared times 1 over x.
Beautiful chain rule. Thank you. So we want f inverse prime of 7. Which would be 1 over f prime of f inverse of 7. What is f inverse of 7? What's f inverse of 7? Good thing, because I don't want to plug any other number into the natural log, right? So then what we need is f prime of 1. (21 times 1 squared) plus 3, what's the natural log of 1? 0. So our derivative at 1 is 21. Okay, please do your best on your homework and help remind me that when we see our seniors, that they should probably watch this 20-minute video